videos mastering eigenvectors and principal component analysis. We learned how to find the hidden axis of data. But there was always a catch. Eigenvectors only work on square matrices. But look at the real world. The data is almost a rectangular. For example, a dataset of 1000 users and 50 movies, a spreadsheet of stock prices over time, and an image. These are all rectangular matrices. They have more rows than columns, or vice versa. If you try to calculate eigenvectors of a rectangular matrix, the math breaks. So, how do we find the hidden structure of any matrix of any shape? The answer is the singular value decomposition. It is the most general and powerful method in all of linear algebra. Welcome to Decoding Complexities. I am Pradeep. Singular value decomposition says that any matrix A can be broken down into three clean components: U, sigma, and V transpose. Let's look at what these represent in simple terms. Matrix U represents the left vectors. This captures the relationships between rows of your data. The matrix V transpose represents the right vectors. This captures the relationships between the columns of your data. And matrix sigma represents the singular values. This is the most important part. It is a diagonal matrix in the middle. It tells us the strength or importance of each pattern found in U and V. Whether the patterns we found are strong signals or just noise. Sigma gives us the answer. This sounds great, but how do we actually calculate these three matrices if the original matrix isn't square? We use a clever mathematical trick. If matrix A is rectangular, we can't find its eigenvectors. But if we multiply A by its transpose, the result is always square and always symmetric. Here is the secret. To find V, we calculate the eigenvectors of A transpose A. To find U, we calculate the eigenvectors of A transpose. To find sigma, we just take the square root of the eigenvalues. So, SVD isn't a new math. It is just eigenvectors applied to squared matrices. We are reusing the tools we already built. Let's see how we can do this in Python. First, we create a simple rectangular matrix with 3 rows and 2 columns. If we try to calculate eigenvalues for this matrix, NumPy would throw an error because it's not a square. But SVD works perfectly. We use NumPy's linear algebra SVD method for calculating this. We get our 3 components. U connects the 3 rows, V transpose connects the 2 columns, and S contains our singular values. One thing to remember here is that NumPy always returns singular values as a simple list of numbers to save memory. If we need to reconstruct the original matrix, we must convert these singular values into a diagonal matrix. When we multiply them back together, we get our original matrix perfectly. The math works. We have seen how to decompose the data, but where do we really use it? Let's take an example of image compression. To a computer, a grayscale image is just a massive matrix of numbers representing brightness. We load this image and run SVD. The singular values tells us how much information is stored in each layer of the image. Let's plot them. Look at this plot. The curve drops very fast. The first few values are huge. The rest are close to 0. This tells us that the vast majority of the image detail is contained in the first few components. The tail end is just a noise. So, let's compress it. We define a function to reconstruct the image. Here, k is the number of components we keep. We slice our matrices to keep only top k columns and values. Then we multiply them back together. Let's see what happens as we increase k. At k equals 5, we are using almost 0 memory. The image is blurry. But we can see the general shapes, the helmet and the background. At k equals 20, the face becomes clear. We are adding more layers of information. And at k equals 50, look at it. It is almost identical to the original. But here is the amazing part. The original image had 512 dimensions, We rebuilt this by using only 50. This is the power of SVD. This brings us to the end of our journey through linear algebra. We started with vectors, learned to project them, built matrices, solved for eigenvectors, and finally mastered the general decomposition with SVD. You now have the mathematical toolkit to understand the geometry of data. But knowing the geometry isn't enough. The real world is messy, noisy, and uncertain. Our models are never 100% correct. They are just probable. To build true intelligence, we need a way to measure this uncertainty. We need to understand the logic of belief. This leads us to the language of science, probability, and statistics. This is the topic of our next series. Link for the companion blog post and collab notebook is in the description. Hit that like button and subscribe to continue decoding the complexities of machine learning. Thank you for watching, and I will see you in the next one.